So let us now turn to the composition of gates. Well, let's first look at it from a very general perspective. So our gates are black boxes that take some initial state and transform it into a final state. And when we compose this with other gates, this is just going to be transformed into another final state, say just like with a prime. Each of these black boxes represent unitary transformations, say U1 and U2. And now we can write our really final state, the one with the prime, as U2 applied to our first final state. And this we can again write as U1 times our initial state. So the composition of this gates is really represented by a unitary operator that is simply the product of these operators. If we carry this out with many of these gates, so apply them all sequentially, we simply get a product of all the corresponding unitary operators. And the main thing of note here is the order of the indices. So for us, time is always running from the left to the right. But when we apply these operators, then they meet the state always from this side. So therefore, the indices come out to be ordered into the opposite direction. And this is something that one really needs to keep in mind when one does these compositions. So this is a very general picture of the composition of gates, but in practice this will boil down to very simple circuits because we are only going to use our single and 2-qubit gates. And let us start with the most simple setting, namely that we only apply single qubit gates. Indeed, let's look at the following concrete example, where we have a collection of quantum bits, and to all of them we apply the Hadamard gate. Because when we look at this, we will see that this is enough to obtain the state capital psi, so the state that we encountered when we discussed quantum parallelism. This is the state which represents all the curly n different numbers within the range of the register at the same time. And indeed we can obtain the state now simply by applying all these Hadamard gates to all the individual qubits in the state 0. So doing so, all of these will be transformed in the following state into this even superposition. And this superposition will simply apply to all of them. And this then simply gives us the separable form of this state that we had discussed at the time. But of course, this also corresponds to the state where we write this explicitly in terms of all the possible states in the register. And in order to see how this really comes about, let's look at this in a little bit more detail. Let me illustrate this for the case of just 2 qubits, because then we see how all our preparatory work in the background sections pays off. Next, we multiply these matrices together. This corresponds to the situation where we apply the Hadamard gate to both of the qubits. By matrix multiplication of these block matrices, we then obtain the following expression, where simply the identity matrices here are replaced by the Hadamard gate. So these identity matrices are basically replaced by the Hadamard gate. And using the concrete expression, we can also write it like this. Just using these block forms here. With this additional minus sign, simply producing these signs in this lower right block here. And this is our most concrete representation of this combination of gates. And now we can check that when we apply this to one of the computational basis states, say 0, 0, which corresponds to the vector 1, 0, 0, 0, This will now simply be transformed indeed into the first column, so into this vector here. And this we can then again translate back to Dirac notation. So it looks like this here. But this is exactly the state in which all the computational basis states appear with the same probability. So this is our state capital psi. So this tells us how the product of all the Hadamard gates acting on all the qubits acts onto this computational basis state. Namely that the result is simply this state capital psi. And similarly, we can also work out what happens when we apply all the Hadamard gates to an arbitrary computational basis state. So not necessarily just zeros for all the different states in the computational basis. And this will simply transform this into a product of all these states, where we sometimes have a plus or a minus sign in front of the state 1. And this simply depends on the value xn of the bit in this binary number here. Now one can actually also multiply it out and write it in a very compact form, which I here just give for completeness. Namely, this can be written as a sum of all the computational basis states. Now this will depend on this value here, which I call x, and the sum of all the different states I'm then going to denote by an integer z, so that we don't confuse the two. In front of this we have again this factor 1 over curly n in the square root. And here we have some factors which are sometimes 1 and sometimes -1, simply coming from the products of all these 1s and -1 at this place here. Now this can be conveniently written in the following way by a special dot product that we define in the following way between two integers with binary representation, namely just the sum of the products of the corresponding entries in these binary representations. So this looks like taking the binary entries in this binary representation, putting them into a vector and just doing the dot product of these vectors. Vectors that simply contain zeros and ones. So this is a result which I just mentioned here for completeness, and we will only return to it at one very specific point later in this course.